In this lecture, we will briefly discuss how we can model friction, how we can measure it, and then we will see some application like power screws, brake discs, and so on. Suppose I have a little box on a surface. Let's say I'll put it on a flat surface. And if I draw its free body diagrams, because this box has a mass m, obviously it has a reaction m. Let's say this is mg. So we'll expect a reaction. Let's call that one n. Now, this thing is at equilibrium. Let's say I apply a load P. When I apply a load P, suppose this box does not move. The principle of equilibrium tells me that there must be some resistive force to balance that load P. So let's call that one F. In this case, F must be equal to P. Let's say we increase the load P, but still the box does not move. The value of F is going to be still equal to P because of the principle of equilibrium. In other words, if I draw a simple graph, let's say on x-axis, I measure P, the load, and here I measure friction. So based on what we just said, I'm going to have a line with a slope of 1, right? Because load P, the friction F is always equal to the load P until that the box start moving. At that point, when it reaches to that maximum, the load F is going to drop, and then it's going to stay no matter how large is the load P. Now, if you look at this graph, this maximum value, we're going to call that one static force or static friction. And when it starts moving, we're going to call that one kinetic friction. So this resistive force that we call it friction, then in this case, can have one of these three scenarios. Before that, reaching that maximum, it's equal to the load P. At the moment that it just slipped, is going to be equal to the F static. And after the motion, we'll call that one, that friction, kinetic friction. And this load F, this friction F is proportional to the normal force. We'll show that by this relation. F is equal to mu n. Therefore, in the static case, I have mu s n, and in kinetic case, I have mu k multiplied by n. All right? So the question is, why this behavior? Why do we see this maximum and then there is a drop? For that, if we zoom a little bit on the surface, let's say I'll zoom on a portion of this surface, and what I will notice, actually, there are some bumps. And these bumps, they come in contact with each other. So our surface is not as smooth as we thought initially. Now, at this contact point, we can imagine there is high stress concentration. There is a chance of plastic deformation. And as a result, we can imagine there is micro welding, which we are not going to go to all these complexity and details, but it tells us that initially I need to have a larger force to overcome and shear these, actually it is bonding between these all little contact points. And after releasing that, then we're going to have a lower actually friction or resistive force. Now that we learn F is equal to mu n, the question is, how can I actually measure this value of mu? For that, all we need is actually an incline. Suppose I have an incline and I put the mass on top of this incline. Now, what I will do, I'll increase the actually the angle of this incline. Let's say the angle over here, let's call that angle theta. I will increase that angle theta until this box start just to slip. Let's make it a little bit nicer. If I draw its free body diagram, so I have the mass mg here. I have the reaction N. Let's call that one N. And of course, I have the resistive force, which is in opposite direction, F. Now, if I find the component of this load, mg, in, let's say, x and y direction, so what I expect to see here, I'm going to have the two components of this mg. One is mg sine theta, and this one mg cosine theta. If I call this direction x and this direction y, sum of all the forces in x is equal to 0, then F must be equal to mg sine theta, and sum of all the forces in y is equal to 0, then N must be mg cosine theta. If I divide these two relations, I'm going to get F divided by N equal to tangent theta. But this F divided by N, already we call that one mu, the friction coefficient. So simply my friction coefficient here, mu, is equal to the tangent of these incline, actually, that angle in that incline. Let's say I have a simple incline here, if you can see it. Perhaps maybe I stop sharing my screen. All right. Let's say we have this incline, and suppose I have maybe on my desk, I have this mass M here. All right. So I slowly increase the slope until it slides. I need to measure that angle. Perhaps I can use maybe my cell phone, or maybe I can just use a simple incline meter to measure the angle. So it's not going to be accurate here, but as a demo, if I'll just show you, if I increase the actually angle slowly until the mass starts slipping. So you notice the angle. So I'm going to repeat it again. I'm going to increase the angle slowly. So that's the angle, let's say 12 point something. And the tangent of that angle gives me the friction, whatever that value is. Let's share my screen again and come back to the idea that we will discuss. All right. Now, let's see some application of friction. In power screws, we will use them to move, let's say, a load W by rotating the screw here. let's say in that direction M, then I can lift that W. If I change the direction of M, the torque that I apply, then I can lower it. Suppose my question that I wish to find out is what value do I need, or what's the value of torque I need to apply here, M, for lifting, let's say, a particular load, W. For that, I need to know some information from this screw. First, I need to know the value of L, which we call that one lead. It means the amount that the screw is advancing in one revolution. Also, I need to know the helix angle, alpha. So the helix angle. And also, I need to know the average radius here. Suppose I know these three values. I apply a load, a torque M, and I wish to know that value if, let's say, we are applying a particular load W here. All right. So when I apply this torque M, obviously the system starts rotating in that direction. So our friction then is going to be in opposite direction. Let's say we'll show it on one of these threads, maybe on that thread here. So that's going to be my friction. And also I have the normal load to the surface. Let's say this is my normal load. I'm just showing the one at one point, but of course there are many contact points on all of these, on some of these threads. We'll just show at one point and we assume that that's the sum of all these forces. So let's say this is my friction and it is equal to mu n. And this is the normal load. Let's call that one n. Now, what I will do, if I write the principle of equilibrium, sum of the forces in y direction is equal to 0. So what I have in y direction is a minus w, the weight. I have n cosine alpha, and I have minus mu n sine alpha equal to 0. That gives me a value of n, which is w cosine alpha minus mu sine alpha. All right. So again, to repeat what I did here, I just found the component of these two loads in the y direction. I'll repeat that one, and I find the component of this load in actually in x direction. So if I do that, let me just quickly show that. So the component of that load here, be a little bit more accurate there. And the component of the other load. So this load is going to be mu n cosine alpha, and this load is going to be mu n, is going to be n sine alpha. Remember that angle is alpha, and this angle also is alpha. So these two loads, they create a moment about the axis. So the moment about the center axis M then is equal to mu n cosine alpha multiplied by the radius plus n sine alpha multiplied by r. If I factor, let's say, n and r, I'm going to have here sine alpha plus mu cosine alpha. I can substitute n with what we found. So we have WR. I need to go back. I will made a mistake here. Here, W is equal to n by that value. So now here, if I replace n, I'm going to have WR sine alpha plus mu cosine alpha divided by cosine alpha minus mu sine alpha. So that's then the value of m we need to actually lift that weight double. All right. Please correct the mistake that we did earlier here. So this is W is equal to N. It was a typo there. And we can always use this general formula. We need to know the value of alpha, which is easy to find out. If I open up one of these threads, let's say, if I open up one of these threads, I'm going to have not that large, perhaps. Let's say we open up one thread. This angle will be alpha, and this length will be 2 pi r, the circumference of the screw here, and this is L. So simply I can find alpha. Tangent alpha is L divided by 2 pi r. In other words, if I know R and if I know L, then I can find out alpha, or I can perhaps measure. Let's solve one simple example together. Suppose here I have a C-clamp, and I clamp these two pieces of wood together. And what I wish to know is if I apply a load, the question says 10 pound, we apply a 10-pound load to the handle at this point. We wish to know how much force actually we are creating or compressing these boxes together there. So that's what we wish to answer. All right, so I need to do some measurements. Suppose I can find the C-clamp, similar C-clamp. Let me briefly here stop sharing my screen and switching to the other camera. All right, so this is the C-clamp that you just saw, and we have the two pieces of the wood. What we want to do, we want to clamp these two pieces of wood. So we rotate this one and we apply our load. Obviously, I apply my load perpendicular to this handle. So when I apply the load perpendicular to this handle, right, then I'm going to create a moment about this actually main axis, which is the force multiplied by the handle length here. So let's say I do the measurement for the handle, and also I need to measure the actually for the screws here, the lead and the radius, or maybe I can refer to the product. Let me go back and share my screen again. And we'll go back to the camera. Wrong camera. All right. Now we're back. All right. So I am back. We did our measurement. And let's say the length of the handle that here we have is 2.5 inches. The lead, we refer to the product, and the lead is 1/8 of an inch. Radius is 1/4 of an inch. So we apply the load, then M will be equal to, if I apply the load, let's say here, then I will produce an M, which is equal to 10 pound multiplied by 2.5, which is 25 pound inch. So that's M. We'll use the relation that we just found. M is WR. We just found it is, I'm going to go back on the slide, sine alpha plus mu cosine alpha divided by cosine alpha minus mu sine alpha. Let's double check, make sure that we write right. All right. So now let's substitute this value. We found the value of M, which is 25. We want to find out how much pressure we are creating, a W here. W multiplied by the radius, which is 1/4. I need to find out the alpha, so I use the tangent alpha is equal to L 2 pi r. We know the value of L, which is 1/8, 2 pi, 1/4. That gives me the value of alpha, which is 4.5 degrees. So I substitute that one here, and friction is given by us. It's given by the question. And let's say we'll go to our, again, catalog. We check the friction between steel and steel approximately, and we'll use the value of 0.4. So 0.4. And here I have cosine 4.4, 4.5, cosine 4.5, sine 4.5. If I do the math from here, I'm going to find out the value of W, 867 pounds, which is a large force actually, all used to clamp it. That's why the C-clamps are a useful device. All right, let's look at another problem, the friction in discs. And a good application of these is the braking disc and so on. And typically they're made out of 2 discs. We apply a compressive load, let's say P, and these discs, perhaps they are rotating in opposite direction. When we apply this load P, it results in stopping one of these discs. Maybe the application is, again, in braking disc and so on. So our aim here is to find a relation between actually M and P and other geometrical values. Suppose I'm looking at this disk surface. Let's say my disk here is going to be a relatively large disk. Now let's look at the small element on this disk. Just going to use maybe a tiny element. Let's say on this disk, which I'm just going to exaggerate a little bit. And this element suppose here is the r and this angle is the theta. So therefore, this arc is going to be, if the radius over here is r, then this length is going to be r d theta, the length of that arc. And now the area, let's say, of this disk, if we call it dA, is going to be r dr d theta. Now, when the disk, let's say, is under a moment m, obviously the other disk comes there, and there must be a friction here, because that little element is in contact with its counterpart on the other disk, and there must be some friction there. So let's call that friction F, and I'm going to do some calculations here. F is equal to pressure multiplied by dA, or is, let's say, be more accurate, it's going to be mu multiplied by N, and N, the normal force here, is pressure multiplied by dA. And pressure in this disk, suppose these two disks has a uniform surface, is capital letter P. So this is the lowercase p divided by pi r squared. Suppose the radius of this disk is r multiplied by dA. So that's the value of F at any little element on this disk. If I multiply this F by R, then it gives me M, obviously. It gives me a small m, right? F multiplied by R gives me the moment about point O, center of this disk. And if I integral all of these moments, the sum of them gives me M. So if I substitute F, P pi r squared dA multiplied by R. And let's substitute. Also, we can take out the constant. P is constant, mu is constant, and pi r squared. Then over here, I have R dA. Now I can write down this integral as a double integral of r dr d theta, which r is from 0 to r and pi is from 0 to 2 pi to cover the entire surface. And this gives me 2,3 mu p r. And that's our final value, which I'm going to write it again here. M 2,3 mu r p. So the amount of moment that we can create depends on the friction coefficient mu, depends on the size of the disk, and of course depends on the amount of compressive load that we apply. And we can use the same principle for other applications like ropes, belts, and so on, which is a discussion for our future lectures. Thank you very much for listening.